Hi, welcome to another video. So today I'm going to be discussing timers. I'll be looking at the specific timers on the Pic18F27K42. I've chosen that device because if you use Microelectronica's software and their timer calculator, it won't help you on this particular PIC. Well, the timers on this particular chip work in a different fashion compared to that of, say, the 18F46K42. I'll show you how and why, so at the moment this timer is running in the background and it's so slow it's going to take hours for it to do anything. If the counter, 8 or 16-bit, has counted up to a predefined value by you, it will generate an interrupt flag, and from that flag you can get it to count, increment something, carry out a function, anything you like. So I like using this device because here's a pen tip. This is the 18F27K42. It can run up to 64 MHz. It's got 6 internal timers and many internal clocks. The one I'll start the initial demonstration, it's a factory calibrated 31 kHz clock. There are some caveats with using timers and SPI combined in the same program. Things to watch out for, but this video is specifically about timers, so I'll keep it just to timers. So I said Microelectronica's timer calculator won't help you. Let me show you why. So if we go Pic18, use the internal clock 500 kHz, timer 0. Let's go for 1 second. 1 second. Calculate. There we go. To turn on the timer, you've got to turn the TO to timer 0 control register, bit 7 hexadecimal 80. You've got to turn that on. Except on this chip, there isn't a TOCON register. It's called TOCON 0 and TOCON 1. So this doesn't work on this chip. Since we want the timer 0 to generate an interrupt, you have to turn on the global interrupts. Now that global interrupts bit 7, is a member of the INTCON 0 register, so interrupt control register 0. The only thing is with Micro C Pro for PIC, you can't type in INTCON 0 bits. Note you get the red line, means it doesn't exist. So INTCON 0 dot, and you get all this rubbish. All these registers are not associated with the INTCON 0, so you have to do a bit more work. So let's type in a G and then press Control Space, global interrupt bit there. Look, INTCON 0 bit 7. So you'd go equals 1. Now I mentioned that, so we've turned on the global interrupt bit here, but it's just easier to do in the Micro C Pro for PIC32. I wonder if they're written by different people. This is a member of that parent register. If you get used to writing bits like this, if you branch out into Android, C++, C# in Windows, and JavaScript, getting used to this being a member of something makes it easier to understand, and it's like second nature if you start early. We have to initialize this timer, so you put a copy of this in the main. It's got 2 timer registers, timer high, which is an 8-bit register, timer low, which is an 8-bit register. Obviously when you use one in 8-bit mode, both in 16-bit mode, we have to enable the global interrupts, enable the timer interrupt bit, and I've got the timer interrupt priority bit also enabled. And here's the actual timer here itself. When we get an interrupt, we have to clear the flag. I had an example here. So the timer interrupt flag, or timer 0 interrupt flag, is a member of the PIR3 register. except these bits don't work. You can preload the registers, I'll go into that in a minute, and then carry out your function. So here I've got it's inverting a valid bit. You can invert a port, or just get it to count, or get it to do anything you like. You put your code there. But you're in an interrupt routine, you're meant to keep the code really short, because during the interrupt, nothing else can happen on your microcontroller. Getting used to associating the registers with a parent register or special function register makes it easier to learn other languages. I'll quickly show you some of the code now so I don't have to come back to it. So the timer calculator said it was timer TOCON. It's not, it's TOCON 0, so bit 7 turns it on. And then bit 4, so remember count backwards, 7, 6, 5, 4. Bit 4, because we've got a 1 there, it's operating in 16-bit mode. If it's a 0, it's 8-bit mode. And then down the bottom to start with, I'm dividing the input 31 kilohertz factory calibrated internal oscillator, dividing it there, which is dividing it by 32,768 to 1. And bit 7, bit 7, 6 and 5 are the clock selections. So for the initial introduction, I've got there 100, low frequency internal oscillator, 31 kilohertz, see page 93. Depending on what page you look, some say it's 32 kilohertz, others say it's 31. But I've got 2 pages that say it's 31 kilohertz on timer 0. Other timers, there are specific 32 kilohertz internal clocks. Right, so here is our timer low and our timer high. I'm using the clock prescaler, so 32,768 to 1. They choose that number because you can buy crystals that run at 32,768 kilohertz. Divide that by 32,768 to 1, you'll get a 1 second pulse, and you can drive seconds, minutes, hours, etc. So that's why they choose 32,768. So I'm dividing that 31,000 kilohertz clock by 32,768, and it's incrementing our timer low counter. And you can see it's happening very slowly, roughly once a second. For anything to happen, this has got to get up to 255, and when it does, that'll roll over from 255 to 0 and then increment this timer by 1. That's got to go from 0 to 255 before we get our flag and we get anything here. So you can see that's going to take a very long time. Let me speed up the clock. Right, that's a bit better, but it's still going to take forever to do anything. That's the clock prescaler, 4,096 to 1. So from that 31,000 a second, every 4,096 of them, we get a 1 here. And that will get up to 255, roll over, and increment this by 1. Let's wait a few seconds. I'm doing this slowly, otherwise you won't understand how it works. So that's it, we've got a 1 here now, and it's got to go to 255 again before we get a 2. So it's still going to take forever to get anything here. Let me speed up the clock again. Well, this is now an 8 to 1 reduction. So every 8 pulses we get a 1 here. And you can now see it's counting or incrementing this counter up quite quickly. Wait for it to get to 255. There we go, we've got a 1 here. So that's an 8 to 1 prescaler. Now let me remove the prescaler, so we've got 31 kilohertz directly to this timer. There we are, that's a bit better. So we go 2, 3, 4, so it's happening quite slowly. It's actually just over 2 seconds to increment this. If I start my phone, give you an example, I've got to plug it in and start my phone quickly to give you an idea of how quickly that's counting or giving us our flag. As soon as I see yellow, I've got to turn this phone on. I think I was a bit slow off the mark. Right, wait till we get to a whole number or a round number. 20, we've got a 10. So let's see what happens at 30. 30, nearly 30, we've got a 15. We get a flag, and this increment roughly once every 2 seconds. Let's see what happens at 1 minute. We should be roughly at 30, 1 minute at 29. So we've got 30 at just over 1 minute. So what's happening here? We've got a 31 kilohertz clock, factory calibrated it says. Then we're dividing it by 256. 256. In the chip it's actually 255 because it counts from 0. So we're dividing it by 256 equals, then we're dividing it by 256 again. Divided by 256 equals, right, so if I go put that into memory, cancel, then 1 divided by memory recall, that number equals, we've got 1 output every 2.114 seconds. Hopefully that makes sense. Right, if we step this up a bit, let's change our clock to 500 kilohertz. So 500,000. Let's say we want an interrupt every, say, 20 milliseconds, 0.02 of a second. So 1 divided by 500,000 equals, it generates a clock cycle every, so that's 1 millisecond there, every 2 microseconds. But we want an interrupt every 20 milliseconds. So we've got 0.2 of a second, 20 milliseconds, divided by our clock cycle frequency, 0.12345 so 2 microseconds, equals 10,000. So 0.2 microseconds goes into 20 milliseconds 10,000 times. We've got two 256-bit registers. So if we divide 10,000 divide by 256 equals 39.062. So 39 255s goes into that 10,000. 256 goes into 10,000 39.062 times. How's that going to help us? And before I forget, that incon0.gie wouldn't compile when I had the bit. You had to cut the bits out, so incon0.gie. Anyway, so time and low increments to 255, then puts a 1 in the high register, and then that counts up to 255 and gives us an output. So if we preload this timer high register, we can get it to count faster. So we want the counter to count 39 256s before it rolls over and gives us our flag, except it's going to count and roll over at 255. So 256 take away 39 equals 217. So if we preload this top register, the high register, by 217, that one there, this one here, that will effectively give us our 39 256s before it rolls over and gives us our counter. And what I forgot to say, so we can check our figures, so if we're getting a flag every 20 milliseconds, what's that into 10 seconds? So we can have a look at the counter. So 10 seconds divided by 0.02, so 20 milliseconds, equals 500. So if I keep the counter on the screen, every 10 seconds we should have a counter of 500. Times 6, or every minute we should have 3,000 counts. Let's go and put it to the test. I'm going to try and power up this device and hit the start as soon as I see the yellow again. Probably a bit slow. So 10 seconds, we're looking for 500. Yeah, just about. And to double check the timing over a longer period, you get greater accuracy. For those people in a hurry, you can skip 30 seconds. So we're looking for 3,000 at 1 minute. So you can see why I started the counter off slowly, so you can see what's happening. But this is 500 kilohertz, 3,000 at 1 minute. Yes, that's pretty accurate. So that illustrates we must be cutting a flag every 20 milliseconds. And you could run a function or do something with that flag. The only other thing left is an 8-bit counter. It works slightly differently. Let me show you. Right, so this is now an 8-bit counter. This timer 0, this low timer still incrementing. But see, we've got a 1 here already. In 8-bit mode, the timer, the low register, will count up to the value preset in the high register. I'll show you what the post scaler does. So this is the 31 kilohertz clock divided by 32,000 times. As you can see, it's really slow. I'll let it roll over once more. There we go. I'll add a post scaler. Right, this should be coming on in a second. Right, watch it when it counts to 9. I've added a 2-to-1 post scaler. 9. Did we get our flag? No. What happens this time? 2-to-1 post scaler. There we go. So that had to count to 9 twice. So the post scaler on this particular Pic18F27K42, it's got a 16-to-1 post scaler. So I could have this count to 9 16 times before it rolls over and gives us our flag. As I say, this is currently a 2-to-1. It's got to count to 9 twice. So I've shown you how to divide the frequencies. You work out the cycle, divide that into your required frequency, divide that by 256 either once or twice, and use either an 8-bit register or a 16-bit register. Hopefully now you've got a better understanding of 8 and 16-bit counters. specifically the Pic18F27K42. If you've got any comments, leave them below. Don't forget to click like if you liked it. Thank you for watching.